Hello, I'm Thor Mortensen. I'm one of the three people on this slide. Um, we're part of the Euroluna team, and the Euroluna team is one of the 30 or about 30 teams that are competing in the Google Lunar X Prize competition. We have a support group with as many as I think 30 individuals, but the principal workers are shown here. There are a few others, but we are those that work the most with this project. From the left we have Palle, we have Søren, and we have me to the right. We realized from the very beginning that we have very little funding except from our own pockets and maybe some funds from the support group, and therefore we would have to find a way to get to the moon very inexpensively. We First of all, we have to keep the weight down because costs seem to be very closely related to weight. Every time you lift something into space, it costs you a certain amount of dollars, and we want to keep that down to an absolute minimum. We have planned two missions. One is a test mission, simply in order to find out whether some of the um, some of the ideas that we have can be realized in practice, and the other one is the final spaceship that's going to land on the moon. I will only describe the lunar lander here, the one we call Romet 3, and we will only I will only describe the actual movement until we get to the landing itself. We have not worked out in detail how we are going to move around on the moon, and that may come in a later presentation. We will as I mentioned before, use fairly inexpensive equipment, which means that we'll use off-the-shelf circuit boards. One comes from the so-called CubeSat family, a series of components for cube satellites. They are 10 by 10. And if we combine them in, say, 3 or 2, we can get a larger satellite, and we can use that for as our spaceship. We also realized quite early that using chemical thrusters would be out of the question, basically, because we will need an awful lot of mass in order to get just 1 kilogram to the moon. I think in one of the early computations we calculated something like 35 kilograms, including the oxidizer, which is a lot more than what we're going for now. Using an ion thruster gives us another challenge, and that is that the thrust is fairly low. We have the design that we're looking at right now. It has a 1 millinewton thrust, and this means that it takes an awful long time to get to the moon. But it still requires 50 watts to run, and since we did not bring any energy with us, all the energy has to come from the sun. So we are trying to be very energy efficient, and we will not produce any CO2 in this mission, at least not when we are on our own. Uh, but we do need about half a square meter of solar panels in order to get 50 watts with the efficiency of the current efficiency of solar panels. We have decided to leave out batteries. They're too heavy. There is maybe a small exception because we need a real-time clock, and in order to make sure that that runs all the time, we have to have a tiny battery that keeps it supplied so that we can always read what the time is and thereby find out where various objects should be. For instance, where the moon should be at that particular time, or where it is at that particular time, and where the Earth is at that particular time. That can be used for several things: attitude control, for measuring distances, and so forth. Attitude is maintained with magnetometers and coils, and at least when we're close to the Earth, we can measure the direction of the magnetic field relative to our own direction, and compare the two and find out what kind of changes should we apply, and then calculate the current. So we need to send through coils in order to get the right attitude. There are two issues that are fairly important here, and that I think perhaps requires a little more explanation than the others. One is the trajectory, and the other one is the landing procedure. And I will go through that in the next couple of slides. As I mentioned before, the ion thruster spits out ions. We have chosen gallium as the metal, basically because gallium is has a fairly low melting point, and therefore we don't need a lot of energy to keep it fluid. The other option was indium, but then we would be required to have a heater that would warm up the tank. It doesn't spend a lot of mass per second, so that's fine. But then it doesn't move it doesn't accelerate very quickly either. So we have two alternatives in order to get to the moon. We could run the thruster all the time. That would result in a spiral going to the moon. It is fairly considering the technology, is fairly fast, but it spends more fuel. It also means that we will be arriving at the meeting point with the moon with approximately the same speed as the moon itself, and we would like our speed to be as low as possible. I'll get into that in a couple of slides. The other possibility is to run the thruster only near the Earth to make an elliptical spiral. That's more economical, but it's slower. The compromise that I have worked out at this point in time is that if we run the thruster about half the time when we're near the Earth, and then we can get to the moon only spending 300 grams, and the speed at the meeting point, which is also the turning point of the resulting ellipse, would be 160 meters per second, not taking into account the gravity of the moon. I'll also get to that in a little while. But it means that the time that will elapse in order to get to the moon is 291 days. I have made a almost freehand drawing here, showing what the trajectory would look like. We would be expecting to hit a point that's opposite the Earth on the center line between the Earth and the Moon, on say in a height of say 500 meters or so, 500 kilometers above the Moon. When we get to that point, our speed relative to the Moon will consist of our own speed and the Moon's speed subtracted as a vector. So we'll get an angle with the ecliptica, the velocity angle to the ecliptica will be somewhere in between 90 and 0 90 and 0 degrees. The idea is then that the trajectory will be with such a speed that we will hit the ground on the front side of the Moon, approximately near the equator of the Moon. Of course, there are things that are not taken into account here. One is that once we get near the Moon, then we're being accelerated by the Moon's gravity. So our own speed will be higher than the 160 meters per second. It will probably be over 1,000 meters per second. And the goal, of course, is that we should find a way to keep that down so that we will actually land on the Moon and not end up in a orbit around the Moon. But we think that can be done. So how are we going to land? If we land with the approximately or more than 1,000 meters per second landing speed, the rocket is not going to look good after that, and therefore we will need to slow it down to a standstill. And we do that by making a tether, so that when we're a long way from the Moon still, we will detach our thruster fuel tank and the solar panels for propulsion in one unit, and the rest of it in another unit, and we will connect the two with a tether, and we'll start rotation in the expected landing plane. Currently we're thinking that we should be able to do it with a tether that is about 1 kilometer to 2 kilometers long. We will accelerate the rotation until the peripheral speed of the lander equals the expected landing speed. And the idea is then that when we get near the Moon, then we could land in such a way that the actual landing speed will be 0 right when we hit the Moon. This is done, seen from the Moon's point of view. The trajectory that the two Romet parts are moving in is going to be a cycloid, and the idea is that at the point when the unit is at the lowest point in the movement, the speed relative to the Moon is actually 0. Sort of like when a wheel is running over a surface, then there is one point on the wheel that is not moving at all, and that's the point that is in direct contact with the surface. And we would, at that point in time, we would cut the wire, the tether, so that the top part will fly away and the bottom part will be sitting on the moon. For that we need some very precise calculations of speed, and we also need to have a good sensor that indicates to us that the moon surface is close to cut the wire at the right time. The one that flies away, the orbiter, will actually move with twice the speed of the landing speed, so that's with about say 2,000 to 3,000 meters per second, and it should probably go into an orbit around the moon and could be useful there. It could also be that we land with such a high speed that it's flying away completely from the moon and we won't see it again. What are the requirements for the landing procedure? We need a tether. We expect it to be between 1 and 2 kilometers long. It needs to have a strength of 1,000 Newton. We have actually just a few days ago talked to one of the vendors of these products, and it seems like it's possible to get that kind of material. The lander has to be fairly well balanced with the propulsion unit at the impact, which means that ideally we would have to calculate very closely exactly how much gallium we're going to bring, so that we can weigh up the two against each other and find out that the weights are fairly equal when we get to the moon. We will also need a near ground detector to cut the string at the right time. I'm thinking of something that would a long string attached to the lander that would sense that it's being hit by the moon's surface and send some sort of signal to ROM it that it now can cut the wire. How near that needs to be, we will have to think about, because obviously we cannot be too high up. On the other hand, we have the advantage of the fairly low gravity of the moon, so we can land with from higher up than we would be able to do on the Earth. And obviously we will need to make very precise calculations of course and speed in order to time this right. And we will probably also need running adjustments, since we cannot be sure exactly whether the thruster is going to keep spitting out with 1 millinewton. Maybe that changes over time, so that it becomes more or it becomes less, and we will need to adjust our running of the thruster from that. What kind of equipment do we have on board? Well, the lander needs to have all the equipment that's necessary for contacting the Earth, sending back video. So it needs a long range radio, it needs solar panel, it needs video and still camera, it needs a navigation and control computer, it needs wheels and electromotors. When I say long range radio, it actually means I will be spending a few more watts on this radio than the other radio, basically because it has to be able to be heard on the Earth and have a reasonable bandwidth when we send pictures down to the Earth. The orbiter needs also a radio because it needs to get commands from us or from the control module, and the only way we can do that efficiently is by using our radio connection. It will also have 3D magnetometers so that it is able to measure the Earth's magnetic field when we're near the Earth. When we're near the Moon, it probably is only ballast. Actually, we can't use it for much. We need the attitude control coils. They're very important for the trajectory itself, but also for the plane that we're going to rotate ROMID in. That needs to be fairly exact also. And we're going to bring maybe a little less than 500 grams of gallium, but we need at least a 300 in order to get to the Moon, and on top of that we need some more in order to get the internal rotation going. We need the ion thruster, we need a tether, and we need a neutralizer. And the neutralizer is simply a device that sends out electrons into space so that a ROMID does not end up getting charged with a negative charge. We have a ground control consisting of a radio and some trajectory simulation software that we have made ourselves. This software is based on Horizon Ephemerides. We thank you very much, the Jet Propulsion Lab, for making these available to us. They are extremely useful for our simulations. The current trajectory simulation software takes into account the gravities of the Moon, of course, the Earth, and the Sun. And so far it has not been judged to be necessary to include other objects in space. But we will probably take into account, or we will take into account, the pressure, the light pressure from the Sun. And this concludes my presentation. I've been honored to make this presentation, and I thank you very much for your attention.